So hopefully by now, writing out a joint probability from the information graph structure should be more or less a matter of just kind of following the edges that your information graph has. In our DAD model, we're summing over all of our hidden variables, kappa, mu, and lambda. But there's actually a term, p of lambda given kappa mu, that couples all three of them. So fundamentally, there's no way we can get those three variables apart. And there's no way that we can factor one of our variables, say kappa, outside of the other summations. So basically what we've got is a big nested expression. I mean, there are certain factors that we can factor, like p of kappa given theta, and that doesn't have to depend upon mu and lambda. But we're still stuck doing all three of these summations basically as nested loops, because we've got this inner factor, p of lambda given kappa mu, that depends on all three of them. So concretely, that's a three-dimensional object that's going to have different values for different combinations of those three variables, and there's just no way to get out of actually summing over the full three-dimensional object. So in this case, in big O notation, that would be a computational complexity of order n cubed. Any questions about that, either in terms of the factoring or the computational complexity?
Yeah, I'm still not clear about the standard procedure to get the factoring answer from the graphic model.
Let me see which part of that you're asking about. Are you asking about how do we write out this list of factors? So going back to our picture here, I can basically just follow my edges, right? So right away I can write p of this entire thing is p of theta times p of kappa given theta, p of mu given theta, p of s given kappa, p of lambda given kappa mu, p of m given mu, p of c given lambda. Okay, so that's the joint probability of the entire set of all the random variables here, right? You were asked to do it just in terms of conditioning on theta. So concretely, that is trivial here, because if I just divide by p of theta, by definition that gives me p of my other variables given theta. Now all I have to do is marginalize out my hidden variables to get what was asked for, namely p of SCM given theta.
What if I just I don't pick up the leaves, I just pick some of the nodes, like S, lambda, and mu in condition of theta?
S, lambda, and mu conditioned on theta.
Or in condition of C, or in condition of M. Is there any standard procedure to calculate theta?
Well, so you know the general chain rule that can give you what you want, right? If you have some set of subject variables and some set of condition variables, you can always get that as being equal to p of the joint of both sets of variables divided by p of the condition variables, right?
Yeah, I mean,
and then you can apply the information graph by basically plugging in the right expressions for both numerator and denominator. In other words, you can translate both numerator and denominator into the right pieces using this information graph, right? If you have further questions about details of that, do you want to go through it in office hours? Because it probably would be helpful to spend a bunch of time going over that derivation. We can do that.
okay, thank you.
Whenever I see you use kappa given theta and P of mu given theta on the answer.
So let's see if I'm understanding you. You're asking,
On the last term over there, the last term, why don't you have the P of kappa given theta and P of mu given theta?
you're asking where is P of kappa given theta? It's right over there.
But that one belongs to the P of S given theta.
Sorry, maybe I'm not understanding what you're asking. So hold on, let's just be clear here about exactly what we're looking at. So what we're looking at is P of MCS given theta equals that. It wouldn't have fit if I put P of MCS given theta. This would have come right off the side. But so is there some part of this equation that you're
Yeah.
wondering about?
Yeah, because the last sum represents P of C given theta, right?
Let me see if I understand what you're asking. So this whole thing is, you can think of it as just being a big joint probability, right?
Yes.
So at some level, because the variables are coupled through that term right there, it's not quite so easy to just call one part of it a particular marginal. I mean, if you want to get a particular marginal, we have to carefully write out, exactly what we get for that marginal.
Okay.
I mean, if you say, for example, P of C given theta, it actually depends on like all these pieces, right?
Yeah.
Because C depends upon lambda, which depends upon kappa, which depends, and mu, which depend on theta. So it's a whole bunch of pieces to get through from theta down to C, right?
Yeah.
So you can write this, obviously. I hope this is obvious. You can take all these summations and you just put them in the front, right? Is that clear that's true, right? All I've done here is I've tried to show, what kind of factoring is possible at all. I mean, for example, I can get this particular term outside of the summation of mu because it doesn't have a mu in it, right? But that doesn't help me at all in terms of the overall computational complexity in big O notation because I've still got this term here that I can't factor out of anything. Are there other questions about the form of this equation? Question.
So I don't know if you answered this already, but why are we using sums? Like, couldn't we just have the equation just set up the joint probability equals those 6 elements, those 6 probabilities, like using chain rule?
Okay, so let's make a really important distinction here. If I had asked you for PMCS kappa lambda mu given theta, then quite right, there would be no summations over kappa lambda mu. But because it's only asking about the probability of the observations given theta, and those observations are connected to each other through kappa lambda mu, not only am I required to have kappa lambda mu in my information graph structure representing them, and then that gives me these kind of factors to get rid of kappa lambda mu in the usual way. We're summing over all possible values of kappa lambda mu.
Okay.
Great question. Other questions? Yes?
Make the road considering one suspect, right?
I think I missed a word here. Something about one suspect.
Yeah, we're only considering one suspect for this, like, with these models. Either that he is or is not the father.
So this thing up here is our DAD model. So this is the model that assumes this one DNA sample that we've taken is from the person who's truly the father of the child.
Okay, so then we consider these two models, but
Well, let me see. I'm actually not quite sure what specifically you're asking, but let me try to relate it to the not-dad model since you raised that. And we haven't talked about the not-dad model yet. So the not-dad model has a somewhat different information graph structure. I think the key thing I want to draw to your attention here is look how S is not tied in to these other variables except through theta, which is the thing that we're conditioning on here. That right away implies the kind of conditional independence that's going to give us factoring, right? Conditional dependence equals factoring, right? So that should hint to you that your computational complexity is going to go down, basically because we've got one piece over here that's coupled. These two variables are coupled, but this one's off by itself. It's not coupled to these two by any specific term. They're just conditionally independent given theta, okay? So when we actually write out the equation here, we've still got summation over all three of our hidden variables. We've got the same hidden variables in both cases. But instead of having a term here that's got both lambda, kappa, and mu all coupled together, we've only got lambda and mu coupled together, okay? So concretely what that means is the terms that have kappa in them don't have lambda or mu in them. That means they can just factor outside of the summation over lambda and mu, and that brings down our computational complexity. Basically, over here, we've got a one-dimensional object, and over here, we've got a two-dimensional object. So in big O notation, you know, if we add sort of a one-dimensional object and a two-dimensional object, our big O computational complexity is still just two-dimensional, right? So order n squared. Any questions about this factoring and computational complexity that we get? So maybe returning to see if I can understand your question. Here we are considering a mystery dad just drawn from the general population. That's why theta is showing up here, right? But that's not making our computational complexity go up, basically because the three hidden variables that are in here that we can't get rid of because they are connected to our observables, one of them is just off on its own separate branch. Okay, so that really helps us in terms of computational complexity because it means instead of three nested loops, we've really only got two nested loops. Other questions? Okay. Okay, so